Hello class. Today we are going to continue on with chapter 2 and we're going to continue on with our discussion of graphs, and we're going to continue. We're going to talk about things like continuity. What does continuity mean? What we're going to do is talk about the basic functions. There are going to be quite a few of them, but they're basic functions that we all know. So we're going to talk about the identity function, squaring, cubing functions, square root and cube root functions, the absolute value function, piecewise defined functions, and then we're going to talk about the relation of x equal to y squared. Okay. So the continuity, what is continuity? So this is an informal definition, and we call a function continuous over an interval of its domain if its hand-drawn graph over that interval can be sketched without lifting the pencil from the paper. That's what we mean by continuous. There's no breaks, holes, jumps of any kind in the graph. That we would call that continuous. So we're going to describe the intervals of continuity for each function. So that means uh, uh, over what intervals is the given equation or function continuous. So for this example here, if we look at the interval on the x-axis, so we're talking about the domain, right? So the independent variable is the x-axis. So we're looking at all values of x in the domain, right? And so in this case here, you could sketch this graph with your pencil throughout the whole number line from negative infinity to positive infinity. Because if you were to stretch out these arrows in both directions, it would go out to positive and negative infinity in the x direction, negative or positive. Okay, so what about this one? Well, notice that here we can draw our graph, and except we have this hole at 3. So 3 can't be included in that continuity. So if we're going to look at intervals of continuity, this graph, or this function rather, is continuous from negative infinity, right? So if we continue this graph, the arrow says it goes on for infinity. So from negative infinity and then all the way up to x equals 3. So we're going to have negative infinity to 3 with the parenthesis, right? Meaning that 3 is not included in the interval. And then 3 is not included, so then it's going to go from 3 to positive infinity. So it's continuous on this interval and on this interval. So basically it's continuous everywhere except at x equals 3. Okay, and we call this a discontinuity. So a hole in the graph, that's a discontinuity, an example of one type of discontinuity. And so in this case here, this identity, right, and this is the identity function, f of x, has a domain of all real numbers and has a range of all real numbers. Okay, so now f of x equal to x is increasing on the entire domain. So it increases from left to right, from negative infinity to positive infinity. And it is continuous on the whole entire domain as well. So the interval of continuity is going to be the all real numbers. So this is all the values of x, right? Talk about the domain. So all the values of x where it's continuous is from negative infinity to positive infinity. Now, what about the squaring function? So this is a squaring function, meaning it's a parabola. And so notice that the domain of this is all real numbers, but the range of this basic function is 0 to infinity. So this is one of the basic functions, squaring functions. So f of x equals x squared. Okay. Some textbooks call these the toolbox functions because all the other types of functions will be can be created by starting with the basic functions or the toolbox functions. Okay, so f of x equal to x squared decreases from negative infinity to 0, so it's decreasing from left to right all the way up to 0, and then it increases from 0 to positive infinity. And it's continuous on the entire number line. Okay. Here's a cubic function. So we're talking about the cube function. So this is the most basic cubic function that we have. And so the domain is going to be all real numbers, as you can see from the graph. Okay. And the range is also going to be all real numbers. So all the y values, there's no holes, no breaks in the graph, so it's a smooth, continuous curve. And so the arrows go off to positive and negative infinity, both in the x direction and in the y direction. It's an increasing function, so it increases on the entire domain. So notice that it's increasing, right? From left to right, it increases, right? So it's an increasing function. And it's continuous because there's no holes in the graph. The root function. So this is the square root function. Okay, so we have the square root of x. Okay, now notice that we cannot have any negative values for x. So that means the domain is going to be all non-negative numbers. So from 0, including 0, to positive infinity. And the range, as you can see from the graph, also goes from 0, right? Because if x is 0, then the square root of x is 0. And if x is positive, then the square root of x is also going to be positive. So this is also going to be from 0 to positive infinity. Okay, and you can see that from the graph of the function. And it's also an increasing on its entire domain. Okay, it's increasing, and it's also continuous on the entire domain. Okay. Now this is a cube function. Now the cube function is slightly different. Notice that this piece here, okay, now the cube function continues on. Unlike the square root function. The square root function just goes in one direction. The cube root function continues on in this direction here. Okay, so it's going to have a domain of all real numbers from negative infinity to positive infinity. It's also going to have a range of all real numbers from negative infinity to positive infinity. It's also increasing, so increases on the entire domain. Okay, it's also continuous on the entire domain. Okay. Now the absolute value function. Okay, so the absolute value function looks like this, right? So it's x here, so y equals x here, and y equals negative x here. Okay, so what happens here? Well, if you look at the domain is all real numbers, but the range is from 0 to positive infinity, so in the y direction. Okay, now it decreases from negative infinity all the way to 0, right? Not including 0, and then increases from 0 to positive infinity. And it is continuous on the entire number line, the entire domain. So now if we want to graph each of these functions here, now these are piecewise defined functions, which means that they're defined over different intervals. So you're basically partitioning the interval. That's why they're called piecewise. You're piecing them together based on the different intervals that they're defined over. So for example, for all x values less than or equal to 2, we're going to use this rule for f of x. For all values of x greater than 2, we're going to use this rule to define f of x. Okay, so there's just two different rules depending on what interval you fall into. Okay, and so we can graph these by just looking at the domains and then applying the rule. Okay, and we can also do the same thing. So all piecewise functions are just defined on the range of values, the domain of each piece of the piecewise function. Okay, so if we look at A, we get something that looks like this, right? So it's a straight line, has a slope of -2 with a y-intercept of 5, so it intersects at 5, and has a slope of -2, so it goes down like this all the way to x equals 2. And notice that we color in with a solid dot at 2. That tells us that 2 is included in this line, this rule here. Okay, that's why it says less than or equal to. Okay, then for all values of x greater than 2, so that's why we have a hole here, because this is the behavior of the graph all the way up to 2, but does not include 2. Okay, and so we're going to have another straight line that has a slope of 1 and and at y-intercept of 1. But again, we're not drawing it all the way to the y-intercept. Okay? So we're going to start at 2, right? So at this point it's 3, but we're going to put a hole at 3. And then it's going to have a slope of 1 that goes off to positive infinity. And this is how you would graph. Okay? And so you see that there is a discontinuity here, a break in the graph, a jump at x equals 2. So x equals 2 would not, it is in the domain of this function, but it again, so this is continuous, okay, on the entire number line, depending on where you're at. If you take both of these piecewise functions. But is it, is it continuous? No, it's not continuous. It's defined, that's what I meant to say. It's defined for all values of x, but it is not continuous because remember, continuity means that we can be able to sketch this graph without ever lifting our pencil off the paper. Okay. Now, what about this one? Now, what we have here is we have a straight line here, and then we have a quadratic here. So we're going to have something that looks like a partial parabola, and then the other piece is going to be a straight line. So it's going to go from 0 to negative infinity for this one, and then everything that's positive for this one. And so this would look like. So at 0, that's when it changes. Okay? Now this is smooth. It is continuous because you can draw this without lifting your pencil off the paper. So this is a continuous function, but it's defined by this here and this here. Now notice that at x equals 0, they both have the same value, 3. Okay? Hold on a second. Something's not right here. Oh, this should be 3. It's a typo. Okay, this is a typo. This should be 3, not 6. Okay, so at both, if these are 0, they both have a value of 3. So that's why it's this one tends to be continuous because of the way it's defined. Okay, so notice that in this case here, it was not continuous at 2. Okay, so now, but notice that from negative infinity all the way to 0, it behaves as like this line with a slope of 2 and a y-intercept of 3. And this one behaves like a parabola that also has a y-intercept of 3 based on here. This should be a 3 again. This should be a 3. And behaves like a parabola that opens downward. Oh, and it has a x-intercept located at where? It's going to be at the square root of what? Square root of 6. Okay, now, here, this is, and it's not quite correct. These symbols aren't showing up. So be aware. The greatest integer function is a box. It looks like a square bracket here and a square bracket here around the x. So again, just be aware these symbols are not showing up correctly. Okay, so this symbol is called the greatest integer function. Okay, again, picture a, here, let me draw it in. So just so that there's no confusion, come on. So it would be something that looked like this. Okay, and likewise, the greatest integer function would look like this. Okay, and so what this means is it pairs every real number x with the greatest integer that's less than or equal to x. Okay, so for example, if I take 1, 1 would be paired with 1. If I choose 1.1, that would be paired to 1. 1.2 would still be paired to 1. All the way up to 1.91 would be paired with 1. So all those would drop down to 1 until you got to 2. And then 2 would be 2. And then 2.1 would go to 2. And 2.3 would go to 2. So that's how the greatest integer function works. Okay? It takes every real number and pairs it with the greatest integer that's less than or equal to that x value. And this is what it looks like. It looks like a step function. Okay? So it looks something like this. Okay, so if we take the greatest integer function and we, again, use our tables, right, we get something that looks like this. The domain is going to be all real numbers, right? It's defined for all real numbers from negative infinity to infinity. Okay. The range of values are going to be all the integers. Every y value is going to be an integer, right? Because it's the greatest integer function. It maps every x value with the greatest integer that's less than or equal to that value. Okay, so from negative 3 all the way to negative 2, all those values in between those are going to be mapped to negative 3, or are going to go to negative 3. And then as soon as it gets to negative 2, it jumps to 2. And then all of these values will stay at negative 2. And then as soon as it hits negative 1, boom, it jumps up to negative 1. And so all of these values are going to be mapped to negative 1. Okay, and so on and so forth. So you get this stair step look to it. Okay, so for the range, it's going to be all of the integer values from negative infinity to positive infinity. Okay, and so this is a constant on the intervals from negative 2 to negative 1, and then from the interval from negative 1 to 0, and then 0 to 1, 1 to 2, and so on and so forth. Notice that the square bracket is on the left here. Okay. Okay, now it is discontinuous at all integer values in its domain from negative infinity to infinity. So every integer, it's going to jump. So there's a discontinuity. So it's only continuous on those intervals from, for example, 0 to 1, it's continuous. And then from 1 to 2, it's continuous. But it does not include the right endpoint in the interval. So now, what if we look at something like this? Okay, so here, I'm assuming these are greatest integer functions here. So it says if x is in the interval from 0 to 2, then y equals 1. If we put 0, then what do we get? We get 1.5, which is going to bring down to 1. So let's paint a picture here. So this is the greatest integer function. Okay. Okay, so then if this is 0, this is going to be 1. Okay, and if it's 1, this is still going to be what? 1. So this will be 1. So if this is 0, this will be 1. If this is 1, this will be 1.5, which is still going to be 1 because of the greatest integer function, all the way up to 2, because at 2, this will jump to 2. Okay, and then 2 to 4 will be the next interval, because if you put 2 in here, you'll get 1, you'll get 2. If you put 3 in here, you're going to get what? You're going to get 2.5. Okay, and then if you put 4, you get 3. Okay, so it has the same sort of ordering pair. Okay, so if you make a table of values, so here's all the x values that they chose, and you write out the corresponding y value, f of x, then you're going to get all these values here. So you get 1s for all these, 2s, 3, and so on and so forth. And so you see the pattern. And so the ordered pairs in the table suggest that the graph below, that the domain is going to be, again, all real numbers, negative infinity to positive infinity, and the range are going to be all of the integer values, from negative infinity to positive infinity. And so you get something that looks like that. Okay, so the greatest integer function will always give you a step function. It is a step function. So now, an express mail company charges $25 for a package weighing up to 2 pounds. Okay, so it says up to 2 pounds, you're going to pay $25 for the package. For each additional pound or a fraction of a pound, there is an additional charge of $3. So we're going to let y equal capital D of x represent the cost to send a package weighing x pounds. We're going to graph y equals d of x for x in the interval from 0 to 6. Okay, so it says for example, again, an express mail company charges $25 for a package weighing up to 2 pounds. So from 0 to 2 pounds, you're going to pay $25. Okay, and then for each additional pound or fraction of a pound after that, it's going to be an additional charge of $3. Okay. So let's put this all together for this interval from 0 to 6. So notice here on 0 to 2, up to 2 pounds, it's going to be $25. And then from 2 to 3, right, that's 1 more pound, you're going to pay an extra $3, so it's going to be 25 plus the 3, which is 28. Okay, and then it's going to stay at 28 from 2 to 3. Now from 3 to 4, you're going to add another 3 pounds. Okay, and so on, right? So what's going to happen is from 0 to 2, it's going to stay at 25, and then from 2 to 3, it's going to jump to 28, and then it's going to jump to 31, and then it's going to jump to what? 34, and then finally it's going to jump to 37. Okay. Okay, so now, again, look at this relation here. Okay, so now we're saying x is equal to y squared. Now recall that a function is a relation where every domain is paired with one and only one range value. So for every x value, for each individual x value, there is only one y value. But in this case here, we've got more than one y value. So this is not a function. It is a relation, but not a function. And so in this case here, it's a parabola that basically is on its side. Okay, and in this case, it opens up to the right, unless of course there's a negative sign outside here. Then it will open to the left. Okay, so this is a sideways parabola, right? So it's a parabola in y now, so in the y direction. And so the domain is going to be 0 to 8, or excuse me, 0 to infinity, right? And then the range in this case is going to be all real numbers. Okay, for the same reasoning that we looked at for squared functions before. Okay, so that is the end of this section. I hope you enjoyed it. I hope it was informational. Please make sure you're doing the suggested homework. Make sure you're reaching out to me for help, and make sure that you practice not only the examples that we went through in class today or in the video, but also some of the examples in the textbook along with the suggested homework. And last but not least, if you have any questions, bring those with you to class. If you get stuck on something, make note of that. Bring those things to class so we can work on them. Anyway, I'll see you then. Have a great day.